Okay, so this is our quadratic equations review. What I'm going to do is I'm going to outline a little bit from quadratic functions, the previous unit, and then go into the specific points of quadratic equations and how we're going to solve for what we're looking for, specifically the solutions to those equations. When we dealt with quadratic functions in the previous unit, what we were really focusing on was this function set either in standard form or vertex form, where either one represent the exact same data, but specifically what the functions are describing is an entire set of data or an entire graph. So specifically, if I was to outline off to the side here, if I draw in a quick graph where x is on the horizontal, y is on here, then we would say our parabola is as follows. Let's say we have the original graph, y is equal to x squared. The point of quadratic functions was, let's take this y equals x squared, or this original graph, and let's shift it to different locations in the Cartesian plane, or the xy plane. So the quadratic functions describe the entire set of data, or the entire parabola, where we're shifting or translating this original f of x equals x squared. Now, there was a bunch of different forms. There was a bunch of different transformations we could apply. We know we did a close study on specifically this vertex form, and we found that from the vertex form, we could get a vertical stretch factor of A. We could determine if A was positive or negative, if there was a reflection or not. In the case where A was negative, we had a reflection, or the graph would be reflected about the x-axis. So just to show as a quick example here, this would be y is equal to negative x squared. A negative is going to flip it over the x-axis. And then we had either a horizontal translation, p units left or right, or a vertical translation, q units up or down. Now, the big key factor from quadratic equations, or specifically quadratic functions, was that it's determining the horizontal translation, p units left or right, it's always determined by the opposite sign of the middle. So what we meant by this was, if I have some general function in vertex form, then if this interior brackets, if the interior was negative or x minus p, we knew this goes right. And then on the flip side, if p was negative, or the p-value itself was negative, it becomes positive within the interior of the bracket, and then we know that that moves left. So the horizontal translation was always going to be opposite whatever the sign of the bracket was. So quadratic functions was taking an original graph y equals x squared and applying transformations to move it within the Cartesian plane. That's what we got to take out away from quadratic functions. And it was all the methods we do, or all the transformations / methods we would use to do that. Now, quadratic equations, they are going to take those exact same two forms. So they're going to take both the standard form and the vertex form, and they're just going to set them equal to 0, because what are we really solving for in quadratic equations? In quadratic equations, the biggest difference is that instead of describing a function in general terms and telling where it shifts from the original graph, what we're doing in quadratic equations is we actually want to solve for the x values that will result in the x-intercepts. So we want these equations equal to 0 to find the solutions, where the solutions are the x-intercepts of the graph. And then to just be more specific of why that's the case, well, if we set the equation equal to 0, or either the standard form or vertex form to 0, so either one of these, if they're set to 0, what is this 0 actually? That 0 comes from the fact that we're saying f of x or y is equal to 0. That's where we're getting that from. So we're saying that when y is equal to 0, when this equation is set to 0, we're solving for the x values that will give us these x-intercepts. Now, there's 3 different ways to ask for x-intercepts in problems. They could either say, what are the solutions? They could say the zeros, or they could say the roots. These are all congruent or equivalent ways of asking for the same thing. So we can say congruent Or if I want to write in mathematical notation of the symbol, I can say a triple equal like that. It's congruent. They're all the same way of asking for x, or they're different ways of asking for the x-intercepts. So you can either have solutions, zeros, or roots. And you're going to see that throughout the practice problems that we do together here, you're going to see that those terms are interchangeable. We're going to see sometimes they use solutions, sometimes they use roots, and then sometimes they'll use zeros, just depending on the problem. But they all describe the x-intercepts of the graph. Okay, so when we deal with quadratic equations, we may find a different number of solutions just depending on the equation given, which is exactly what this line says. So depending on the quadratic equation, we may find a different number of solutions depending on the equation. So we may either have two solutions, one solution, or no solution because it does not cross the x-axis. So to get this from our quadratic equations, to get our roots, zeros, or solutions, there's going to be potentially some different methods here to get them from the quadratic equations. I'm just going to break them apart to keep this simple into methods 1, 2, and 3, and that should help us out here. So method 1, specifically, we're going to go over graphing, how to get these things from graphing. And what it means by graphing is, let's type this into our calculator. Let's type in a problem or a quadratic equation into our calculator and see what the result is. So to get the graph of this one, first of all, our first step is to go, let's type this function or the starred function into our y equals. So we're going to click y equals, or the top left button on your graphing calculator. I'm going to type in that starred function. When I type in that starred function, your next point or your next step will be to say second button or the blue button, and sometimes it's orange depending on the calculator, second, and then graph, which doubles as the table button. When I do that, I'm going to be given a table of values where I can draw the graph very easily just based on the points I'm looking for. So the points you're going to be looking for are when y is equal to 0, because remember, in quadratic equations, we're setting the y equals to 0 or the f of x equal to 0, and then trying to find the x values that satisfy that equation, which are our x-intercepts. So you want to look for where y is equal to 0 in your table of values. From this function, I see that the table of values says I have a 0 at -5, 0, and I have 1 at -3 and 0. Now, if I want to draw the rest of the graph just to have the picture, what I can do is look at the rest of the table, and I would say my vertex is -4, -1, and then I'll just draw the next 2 points that are above our x-intercepts. So we have one at -2 and 3, and the other one at 6 and 3. All that's left to do is just draw our completed parabola with our arrows on the end here. And now that we have the arrows on the end here, we're fine to say that that is a completed graph. Okay, so now our third step is what they were really asking for. They said, what are the solutions? What are the solutions to this specific quadratic equation? Well, the solutions are going to be where it crosses the x-intercept, or it crosses the x-axis, which are our x-intercepts. Those occur when x is equal to -5 and x is equal to -3. And I could take this a step further and write it in point notation. However, you will not be required to do this. So I have -3 and 0 and -5 and 0. And that just means in terms of x and y, that's what those points are. But they would be asking for these specifically, where x is equal to -5 and x is equal to -3. Those are our solutions to the graph. Now here's a prime example of what they would do by just switching the terminology just ever so slightly. Find the zeros. Well, we know that the zeros also mean the solutions or the roots, because they're all interchangeable. So we have the solutions or roots to the following quadratic equation. Very similar. What I'm going to do is I'm actually just going to enter this into my graphing calculator, and I'm going to find from the table of values or specific graphing functions how to get these zeros. I'm going to walk you through how to get them using the intercept form, which I think might help you get them equally as fast as the table of values. So what we're going to do is I'm going to star my function again, because my first step is I'm going to enter that function into y equals. I'm going to enter it into the y equals. So I'm going to press y equals and then enter the starred function. From there, what I want to do is I want to say, let's type in second, then trace value, which is going to be our fourth button on the top, second trace. And now what I can do is I can either do intercept or zeros. I would say, just for the sake of this, I'm going to do zeros, but you can always do intercept. The only difference would be if you want to do intercept instead. So suppose I said intercept here. What I would have to do is I would have to set my second y2 or my second y function equal to 0, because then I can do the intercept. But if not, if I want to do the second trace, then we have to remember my left bound and right bound, and then we can get these two. So when I do that, my solutions I should get are x is equal to 1/4 and x is equal to 1. Those should be your two zeros, solutions, or roots, whatever you want to use in that case, but based on the problem they asked for the zeros, so we're going to classify them as zeros. And just as above, what we could do is we could always enter them into point notation. So we could say 1/4 and 0, or 1 and 0, where the 0 is just representing the y value. We're crossing the x-axis at this point. Now, method 2 to solve these equations and get the x values would be factoring. Now, factoring is the first algebraic method because the first one was graphing. That's not considered algebraic. Algebraic would be starting at factoring. This is our first available method to solve for solutions, which are the zeros or roots. Now, there's a couple different forms of factoring, which becomes really important that we distinguish a certain amount of steps or specific steps that you can follow so that you can solve these. Step 1, if we're following our steps to solve using factoring, what we're going to have to do is, first of all, we have to remove a common factor. If there's available common factor, it has to be removed right away. Because in the case of the example below, this 4x squared plus 8x equals 0, when we remove a common factor, this is actually in its simplest form now. We don't need to further factor this. So if we can remove a common factor, sometimes you'll be done right away. Other times you will need to use either decomposition or some form of further algebraic step. But in this case, we actually get our factors right away. Step 2 is to count the number of terms. If we count the number of terms and we see that there's 2, it's most likely a difference of squares. If we count it and there's a number of terms is 2, it's most likely a difference of squares. That's super important because oftentimes, unless it's like the one in the step 1 where we have an x squared and an x, we know that that would just reduce to some common factor, and then we don't have to do any like true factoring or decomposition. It would be done as soon as we pull out the greatest common factor. But in most cases, if you see 2 terms, it's most likely a difference of squares. And so you're going to be given the difference of squares formula. You don't have to memorize that. What you do have to know, though, is that you have to recognize that if you have these 2 terms, how am I going to get a difference of squares from there? And we're going to work on further examples below, but I just want you to be aware that if there's 2 terms, it's most likely a difference of squares. Now, if there's 3 terms, then we must put the quadratic into the form ax squared plus bx plus c equals 0, then solve for the solutions. What do we call this? Well, we would say it must be in standard form from what we know above. Standard form, which represents this ax squared plus bx plus c equals 0. Now, we have 2 case scenarios if we have the 3 terms and it's in standard form. We have to look to the a value because the a value tells us everything about how we solve these. If a is equal to 1, then our factors just directly come from our sum and product. So as a quick example, we can say if x squared minus 3x minus 18 is equal to 0, we always multiply to make the outside terms and then add to make the middle term, which is negative 3. In this case, if I was to draw my x that we did multiple times in class. If I draw my x, I'm going to multiply to make negative 18 and add to make negative 3. My factors were 6 and negative 3. And so I can just take them right from there and write them into our table, or write them into our factors using the signs that we discovered from the sum and product method. And then they just go right into that, and we consider this a factored form. If they ask for a quadratic equation to be factored, they want it left in this form. Now, if a does not equal 1, this is our second case here. If a does not equal 1, then our factors must come from decomposition. Okay, so we perform a very similar step here. We start by drawing our x, and we say, what's going to multiply to make that negative 10, or the product of the outside? So negative 5 times 2, that's going to be negative 10. What multiplies to make negative 10 and adds to make negative 9? Well, I found that those were negative 10 and a positive 1. But remember, we can't just jump right into the factors like we did in the previous question because a doesn't equal 1. Therefore, we're going to have to do some form of decomposition where we write out our same terms, but then have to group them in ways that will allow us to pull out a common factor. And you're going to see that in the examples below, but you just need to be aware of if a does not equal 1, we have to do decomposition. Now, just an important note, this refers back to what I just said in where is a equal to 1, or the first step there. I said, if the question asks for the factors of a quadratic equation, they do not want you to give specific x values. So that's a very common mistake where people, or students specifically, will give the x values, which, yes, that's technically right, but when they say factors, they want you to leave it as a set of brackets. So similar to above here, it'd be, if I left it as the factors, it's x plus 6, x minus 3 equals 0. That's our leaving as a factor. Now let's try a first example below here. They give us a quadratic equation of x squared minus 9x plus 8. Then find the solutions. So we have to factor the quadratic, then find the solutions. If I factor this, I know I'm going to have to be left with factors that are equal to 0. First of all, I'm looking at the a value. A value is equal to 1 here. So if a is equal to 1, we do not have to do decomp. We do not have to do decomposition. Now I get to draw my x. So if I draw an x here, it's what multiplies to make 1 times 8, which is 8, and adds to make negative 9. Multiplies to make negative 8, or what multiplies to make 8 and then adds to make negative 9, I would argue that that's going to be negative 8 and negative 1. Because negative 8 times negative 1 will give us a positive 8 back again. But then negative 8 minus a 1 gives us negative 9. Now what can we do? We can go right from our x's here, or our factor x, and what we can do is just sub them each in. We can say x minus 8 and x minus 1 is equal to 0. Boom, that's our factors. So this is the factored equation. Now, what they ask for is then they say, find the solutions. Now, solutions can also stand for roots or zeros. Remember, these three terms are all interchangeable. Roots, zeros, or solutions. In order to find, if I know my factored form, what I can do is I can actually separate my factored form into two components equal to 0. I can have my one factor equal to 0, so I can have x minus 8 is equal to 0. And then I can have my second factor equal to 0, x minus 1 is equal to 0. Now it's just about isolating for that x. If I want to isolate for the x, I'm going to add the 8 to both sides, and I'm going to add the plus 1 to both sides. Now that's going to leave me with x is equal to 8, and then x is equal to 1. And these would be considered our roots of the equation or our solutions. So these are the solutions, And in quadratic equations, what do we mean by solutions? We mean it's the x values or the x-intercepts. So where y is equal to 0, we have our x-intercepts of x is equal to 8 and x is equal to 1. Those are our solutions to this quadratic equation. Try another example here. We have factor the quadratic equation 3x squared plus 9x minus 12 is equal to 0. Then find the solutions. So if we want to first factor this, what we're going to have to do is draw our factoring x. I know that from our equation, a does not equal 1. So what does that mean we have to do? We have to use decomposition. Now, I need two numbers that multiply to make 3 times negative 12, or negative 36, but then add to make 9. Well, from that, I would say we have 12 and negative 3, because 12 times negative 3 is going to be negative 36, and then 12 minus 3 is just 9. But now we need to use decomposition, so I'm going to draw my arrow over, and I'm going to write in 3x squared plus 12x minus 3x and minus 12 is equal to 0. Notice that 12 minus 3 is going to give us back that 9x. So we've kept the exact same function. We've now just separated it into a first step that will allow us to get its true factors. Now, what I did in class is I grouped the first two terms and I grouped the last two terms. Don't mistake these brackets as multiplication. It's just a way to organize this so that you can pull out common factors from both of them. What can I take out of the first one? Well, I would take out a 3x, which is going to leave me with an x in the brackets. If I take 3x off of 12x, I'm just going to be left with 4 on the interior. Now, the second set of the second pair, I can take out a negative 3 from both of them as the greatest common factor, leaving me with x plus 4 in the brackets. And this is equal to 0. Now, what do I have to do? I have to take the outside terms and pair them together, and then I have to take one of the common bracket. We have x plus 4 written twice. We only need to take it and write it once. So we have 3x minus 3 with x plus 4 is equal to 0. This is our factored form. That's our factored form for this quadratic equation. Now off to the side, let's discover what the specific solutions are. The solutions, which are also the zeros and they're also the roots. If we take each of these equations off to the side and we set them equal to 0, just as we did in the last question, if they're both equal to 0, then if I use algebraic steps to isolate them, I can get the solutions to this, or the x-intercepts. Well, 3x is equal to 3 if I move the 3 over to the right side. And then if I divide by the 3, I get x is equal to 3 over 3, which is just 1. And if I subtract 4 from both sides on x plus 4 equals 0, if I subtract 4 from both sides, I'm going to get x is equal to negative 4. So these are my solutions to the quadratic equation. Is x is equal to negative 4 and x is equal to 1. Now, remember the note specifically outlined in the above notes. What we said is when we're dealing with factors, if we see that a function has, or a quadratic equation has two terms, it's most likely a difference of squares. In this case, I would agree with that assessment. In this case, we have a difference of squares. And what we do is we know that difference of squares is written as a squared minus b squared is equal to a plus b and a minus b. Now, what is a squared and what is b squared? I'm going to classify just based on the problem. I'm actually going to write this one, or the 4x squared. This one will be my a squared, and 1 will be my b squared. If I want the singular versions of each, I'm going to say 4x squared square rooted is equal to, well, this is going to be 2x, And that's our singular A. And then I'm going to take my 1 and I'm going to square root that. So I go square root of 1, and that's equal to 1. And this is my singular B. So now if I want to write in my factored form that's equal to 0 because it's still a quadratic equation, I can now write this as 2x plus 1 with 2x minus 1. And this is equal to 0. So I guess we wouldn't need to technically write the equal sign on the left-hand side there. We can just say 2x plus 1 times 2x minus 1 is equal to 0. And this is our factored form. This is our factored form. So we've factored the quadratic equation. Now we need to find the solutions. Well, we're just going to do the exact same thing as we've done before. We're going to take this equation here. We're going to set each of the factors equal to 0 and then solve for the x values. On the first one, 2x plus 1 equals 0. If I move the 1 over and then divide by 2 on the x, I'm going to get x is equal to negative 1 over 2, or negative 1/2. And then on 2x minus 1 equals 0, if I plus the 1 to both sides and then divide by the 2, I'm going to get x is equal to 1/2. So I get x is equal to negative 1/2 and x equals positive 1/2, and then these are considered the solutions to my quadratic equation. What if the solutions, roots, or zeros are given at the beginning and they say, let's make a quadratic equation? Now we just have to work in reverse. If we're given the solutions, then let's work backwards and see if we can construct this equation. So with each of these, I know that to get the specific root, I had to isolate for x. To undo that, what we're going to do is take this first one, x is equal to negative 1/2, and to get this all to one side, or to get it all on the left-hand side of the equal sign and set it back to 0 so we can get our factor, I'm going to multiply both sides by 2. So I'm going to multiply both sides by 2. That's going to effectively cancel the 2 from here, and we're going to get 2x is equal to negative 1. Now I have to add the plus 1 and add the plus 1 to both sides. That's going to give me 2x plus 1 is equal to 0. There's our first factor, and we can even include in brackets so that we know that it's a factor. The second set of brackets we have, or the second 0 or root, we get x is equal to 4 over 3. To do the same thing to get everything on that left-hand side, I'm going to multiply this all by 3, which is going to cancel the 3's there. I get 3x is equal to 4. Now I have to subtract 4 from both sides, and I'll get 3x minus 4 is equal to 0. Awesome. So now we have our two factors. We have 2x plus 1 and 3x minus 4. Let's put these together and see if we can expand this. We have 2x plus 1 and 3x minus 4, and this is all equal to 0. Because if they're independently equal to 0, then together they can also be equal to 0. I'm going to FOIL this, so I'm going to apply 2x times 3x, and 2x times negative 4. That's going to give me 6x squared minus 8x. My next two, I'm going to say 1 times 3x and 1 times negative 4. That's going to give me plus 3x minus 4, and that's all equal to 0. My last step is just to combine the common terms. We have two common x terms. So what I'm going to say is I'm going to rewrite this as 6x squared, negative 8x plus 3, that's negative 5x, minus 4 is equal to 0. And therefore we've undone the steps from factoring it to getting the zeros. Now we've taken the zeros and put them into a quadratic equation in standard form. Now the biggest key I'll point out is that if you're ever given a fraction as a root, make sure you're not just plussing that fraction over. So a common mistake might be to say, let's take that first root of x is equal to negative 1/2. It would be bad to write it as x plus 1/2 is equal to 0. Although it is still correct and it's still the same technical solution, that will lead to issues with the distribution because then you're dealing with fractions up in this component towards the top here. You would have to start applying fractions instead of just applying whole numbers, which can sometimes be easier to simplify. Now method 2, so we had method 1, which is factoring. Method 2 is going to be completing the square and using the square root principle. So suppose that we look at this first example here and they say solve the quadratic equation using the square root principle. What they mean is that we're taking this function that looks like it's in vertex form. So we can almost say this is vertex form. If we want to take something that's in vertex form or something that's already been completed, or completing the square method has already been done on this, let's just use our square root principle to get the x values or to get these specific roots of the equation. So they say solve the quadratic equation by using the square root principle. I'm going to take 2x minus 2 squared minus 50 is equal to 0. So I've just rewritten the equation. I'm going to add the 50 over. So now I have 2x minus 2 squared is equal to positive 50. Then I want to divide by 2 to get x minus 2 all squared, which is equal to 50 over 2, and that's just 25. Now I can square root to get rid of the squared on that term, or the left-hand term. I get left with x minus 2 is equal to plus or minus, because if we square root when we're solving for these roots here, we have to add a plus or minus. And what is square root 25? That's going to be equal to 5. So we have x minus 2 is equal to plus or minus 5. Now this is where we have to separate it into two cases. Case 1, or case number 1, we can choose it as either one. We can say this is where x minus 2 is equal to plus 5, or we can set it as x minus 2 is equal to negative 5. I'm going to set it as x minus 2 is equal to 5 as case 1. And if we want x alone, we would add the 2 over. Thus, our one solution for this is x is equal to 7, because 5 plus 2 is equal to 7. Now, case 2 is taking the negative. Case number 2, we want to focus on the negative 5. So x minus 2 is equal to negative 5. And if I add a 2 to both of these sides, so if I go plus 2 and plus 2, I'm going to be given x is equal to negative 3. So our second solution here is x is equal to negative 3. And so when they say solve the quadratic using the square root principle, they want you to isolate for x. And then if possible, in most cases, we're going to have to use the square root principle, which means we have a plus minus. This is so critical because the plus minus is what sets up those two cases. And if you don't put a plus minus, you'll only get one case or one of the possible roots that you need. And that's technically only half right. So if you see anything that's talking about solving a quadratic using a square root principle, you're going to assume that that plus minus is going to give you these two cases we're looking for here. This one says, solve the quadratic equation with the square root principle, but then gives you an equation in standard form. This is in standard form. So we have a method of converting between standard form and vertex form, and it's called completing the square. So if you ever see a question that says solve the quadratic equation with the square root principle and it gives you something in standard form, we know we have to do something in vertex, or we have to take that standard form and convert it into vertex form first. We're going to complete the square on this. So I'm going to rewrite our quadratic function, or quadratic equation, is equal to 0. Our first step was, is the a value greater than 1? If it is, we need to factor something out. If it's just 1, we can just keep it as it is. We know in this case, a is just equal to 1. If a is just equal to 1, we can just start right away. So I have b over 2 squared is equal to, b in this case is negative 8 over 2 squared, which is equal to negative 4 squared, which is equal to 16. Now let's just clearly keep track of this, because this is going to play a large role in how our final solution looks. I can now rewrite out my x squared minus 8x. Now I'm going to plus and minus the squared term. So the plus and minus the 16 minus 4 is equal to 0. Which terms make up my perfect trinomial? It's the first three we've assembled. So that includes the plus version of our squared term. Now, where does our factor come from for our perfect square trinomial? It's from the part outlined in blue. It's from that part that's just before we square. That represents our factor, and in fact, we actually carry the sign with it. So we can write this as x minus 4 and x minus 4. Then negative 16 minus 4 is just negative 20, and that's all equal to 0. Anything that's written out the same time twice and multiplied, we can just say is x minus 4 squared minus 20 is equal to 0. Now we can apply our square root principle because we've completed the square. Now we can take this vertex form equation and use the square root principle to solve. So I'm going to write this as x minus 4 squared is equal to 20, because I'm going to plus 20 to both sides. Now I can square root both sides, and I'm left with x minus 4 is equal to root 20. Now we have two cases here. Because root 20 won't directly simplify, or I guess we could simplify it, let's simplify this into a mixed radical. The largest perfect square that can fit into 20, that's going to be 4. So I can rewrite this, and you can check the work on this, but I'm going to rewrite this as 2 root 5. We have plus minus 2 root 5. Case 1, if we have case 1, let's choose this as the positive. X minus 4 is equal to 2 root 5. It's the positive. So therefore, one of our x values or solutions is x is equal to 2 root 5 plus 4. And we could either simplify that into a decimal or leave it as that. Either would be okay. And they may specifically ask for a certain way, but in this case, we're just going to leave it as that. Case number 2. Well, case number 2, we're just going to take the negative. So we're going to go x minus 4 is equal to negative 2 root 5. If we move the 4 to the other side, we're going to get x is equal to negative 2 root 5 plus 4. So both of these cases, they give us a final solution that represents the 0 solution or root. And this would be solving it using the square root principle. Yet again, to reiterate, if we have a square root, we know that this plus minus has to exist because that's the part that sets up our two cases. The plus minus is what's going to give us these two individual roots. Okay, and our third and final method for finding the zeros, roots, or solutions is going to be using the quadratic formula. So one thing I want you to note about the quadratic formula is that this method is guaranteed to find solutions of quadratics, or specifically quadratic equations. If you cannot factor, then oftentimes you can resort directly to this one and it's going to give you those factors. So just realize that if you're ever dealing with an equation or a quadratic equation where it doesn't want a factor on surface level and you can't use just the basic factoring methods, know that the quadratic formula is a surefire way to get exactly the solutions you're looking for. So let's consider the example 1 here. We have an example where it says solve the following quadratic equation and then leave your answer in simplest radical form if necessary. Our first step of solving for the solution to the quadratic equations is going to be move all the terms to the one side to make our equation in standard form. So if we want an equation that looks like ax squared plus bx plus c is equal to 0, well then I'm going to move the negative 12x and the 15 over to the other side using subtraction. So I get 4x squared minus 12x and then minus 15, and this is all equal to 0. Now what we have to do is label our variables, because that's going to help us plug it into the quadratic formula. A is equal to 4, B is equal to negative 12, and then C is equal to negative 15. So if I plug this into my quadratic formula now, I'm going to get the quadratic formula is x is equal to negative b plus or minus square root b squared minus 4ac all over 2a. Plugging in the values, I get negative 12 for b plus minus the square of negative 12 minus 4, and then a was 4, c was negative 15, and this is all over 2 and times 4 for a. So I get 12 outside, because a negative and negative is equal to the positive, plus or minus the square root of 144, because 12 squared is 144. And then that second term is going to be, it's going to be negative 240, but because we have two negatives, it's going to be plus 240. And this is all over 8, because 2 times 4 is going to give us the 8. Okay, so now we can write this as 12 plus or minus square root, well, 144 plus 240, that's going to give us 384, and over 8. The largest perfect square that can fit into 384, that's going to give this as 12 plus or minus the square root of 64 times 6, all over 8. Which this is equal to 12 plus or minus, well, if we square root the 64, that gets taken outside of the square root, and we leave the 6 all over 8. Now we can simplify this if all three terms can simplify. What I mean by that is we're going to have all three of our coefficients be able to be simplified using a greatest common factor. If only two of them can simplify, you can't do that. So I can't have just 12 and 8 simplify or 8 and 8 simplify. It has to be all three. It's all or nothing. Even if you have to write that as a note to yourself when you're studying here, say all or nothing. It's all / nothing. You can't take one grouping. It has to be all or nothing. In this case, when this simplifies, I get it simplified to, well, 8 can be simplified, or specifically a greatest common factor of 4 can be simplified from all of these. So what I'm going to do is greatest common factor that is shared between 12 and 8 is going to be 4. So what we can do is we can say this is equal to 3 plus or minus, well, 4 off of 8 is 2 root 6 over, and we remember we took off a greatest common factor from all three of these terms. So 12 over 8 reduces to 3 over 2, and 8 over 8 reduces to 2 over 2, according to the fact that we have a common term of all of those. So now my two solutions, I have case 1, which is going to be where x is equal to 3 plus 2 root 6 over 2. And then my second case where x is equal to 3 minus 2 root 6 over 2. Those are my two solutions according to the quadratic formula, and I could simplify them. I can't simplify them anymore from there because we've already reduced the terms, including simplified the radical. So those would be our two roots of our equation. Okay, and then this should be noted that we've discussed three methods now. We have factoring, we have completing the square and using square root principle, and then we have the quadratic formula. These three methods can all be used to solve quadratic equations, but depending on the problem, one method may be better than the other. One method may be better than another. And this would occur when, if factoring fails and you can't form two distinct numbers, supposing, like, let's consider our last example. We got solutions of 3 plus 2 root 6 over 2 and 3 minus 2 root 6 over 2. Those aren't going to be even, easy numbers for your roots. So it would have been better to use the quadratic formula in this case, because we couldn't have come up with those roots specifically algebraically, other than using the quadratic formula. Now, the last component we've worked through was characterizing the solutions that we get, and this comes from the discriminant, where we can determine the nature of the roots. So if we want to consider the discriminant, this will help us classify what type of solutions we have or the nature of the roots. So depending on the value we get for the discriminant, this classifies our solution and tells us what the nature of the roots are. Let's consider an example here. So if we know that the discriminant comes from the quadratic formula, where in the quadratic formula we have negative b plus minus root b squared minus 4ac all over 2a, well, the discriminant actually just equals to the root here, everything that's under the root. And depending on our result of the discriminant, whether it's greater than 0, equal to 0, or less than 0, that tells us a lot about, do we have two real and distinct, two real and equal, or no real roots? Or does it cross the x-axis twice, once, or no times? Example 1 here, and we'll see if we can classify this one, or classify and determine the nature of the roots. So we can either say classify the roots or determine the nature of the roots and then classify the number of roots. First step is we're going to have to make sure everything is on one side of the equal sign. What I'm going to do is I'm going to rewrite our quadratic equation as 4x squared plus 12x and then plus 9 is equal to 0. And that was from adding the 9 to both sides so that we can get the 9 off of the right side and into the left. Now that we have it in our general standard form, what we can do is we can write out, if we're considering the discriminant is what we can use to help us determine the nature of roots. The discriminant is equal to b squared minus 4a and c. So by classifying each of our a, b, and c, where a is equal to 4, b is equal to 12, and c is equal to 9, let's sub these into our discriminant and see what we get for our value. The discriminant is equal to 12 squared minus 4, a was 4, and c was 9. So we get a discriminant value, which is equal to 144 minus 144. And if we get a discriminant that's 144 minus 144, what do we have? We have, therefore, the discriminant is equal to 0. So if we reference our specific options, so we have two real and distinct, two real and equal, and no real roots, if the discriminant is equal to 0, we have the middle case. So therefore, if the discriminant is equal to 0, we have two real and equal roots. So we've determined the nature of the roots. They're two real and equal, but then that also means we can classify the number of roots to be two roots. Using the discriminant, we've been able to classify the nature of the roots, and we've also been able to classify the number of roots. We have two real and equal roots based on the fact that we have a discriminant equal to 0. So that would be our answer here. D is equal to 0, so we have two real and equal roots. Now consider this example. It's a little more abstract, but it looks for the abstract case where it says, for what values of k will the quadratic equation x squared minus 8x plus k equals 0 have two real and distinct roots, two real and equal roots, or no real roots imaginary? What we have to do is we have to outline the three cases we have. So if we want to focus on the discriminant to help us solve this, the discriminant when we have two real and distinct roots is equal to, discriminant is equal to b squared minus 4ac, which is greater than 0. It's a positive value. For two real and equal roots, we say that b squared minus 4ac, well, just like the last question, must be equal to 0. And then finally, for no real roots, we're going to have b squared minus 4ac is equal to 0. And that means that the root is negative. And if the root's negative, then this can't exist. More explicitly, if we get a negative here, well, a negatives can't exist under a square root. So we know that this is no real roots or imaginary as soon as we get a negative value. Now let's classify based on our question here. What are the A's, B's, and C's? Our A is equal to 1. Our B is equal to -8. And then the C value is just K. And K is what we're looking for here. It says find the values of K, where the quadratic will have 2 real and equal, two real and distinct, or no real roots. Let's start back at part A here. Let's sub in what we know. We know -8 squared minus 4a was 1, and c was just k, is greater than 0. -8 squared is 64, and then we have minus 4k is equal to 0, or greater than or equal to 0. Now, if I move this over, so if I go plus 4k, that algebraic step will isolate k on the other side, so 64 is greater than 4k. And now if I divide by this 4, therefore, we get 2 real and distinct roots when k is less than 64 over 4. In this case, we can say is equal to 16. So when k is less than 16, we know we have 2 real and distinct roots. In the second part, we have -8 squared minus 4, a was 1, c was k, is equal to 0. That means we have 64 minus 4k is equal to 0. If I add the 4 over just like we did on the last problem, then I get 64 is equal to 4k, or therefore k must be equal to 16 in order to get 2 real and equal roots. Okay, and finally, we can plug in the numbers the exact same ways as we've done before. So -8 squared minus 4a, which is 1, c, which is k, is, this is supposed to be less than 0. We have 64 minus 4k is less than 0. I'm going to move that positive k over, or the positive 4k. I'm going to get 64 is equal to 4, not equal, is less than 4k. And if I divide by 4 to both sides, I get therefore k is greater than 16 if we want no real roots or imaginary roots. So these would be the solutions here. Now, just as a teachable moment, suppose we consider the first example we had again. I'm just going to write as a secondary option, so number 2, suppose that we instead said 64 minus 4k is greater than 0. If I instead move the 64 over, so I said -64 minus 64, and then my next line is minus 4k is greater than -64. If I divide by a negative, so if I divide by a negative value here, and I get a solution, I have to flip my inequality. So this now becomes k is less than 16. Because anytime I divide by a negative, if I divide by a negative, I'm going to have to flip the inequality. So I'm going to specifically note that. Flipped, because we divided by a negative value.